Hello everyone and welcome to the next episode of GPU Programming with TNL. In today's video we will talk about parallel reduction. In the last episode we explained the parallel for function in detail and mentioned that it can process independent tasks in parallel using lambda functions. We also noted that parallel for is not suitable for operations like summing a series of numbers or similar operations. This image, which we also saw in the last episode, shows that the variable sum is where parallel threads can interact, leading to an unpredictable and incorrect result. Reduction or parallel reduction is designed for such situations. It is an operation that takes a set of elements as input and outputs one or just a few values. Examples of operations requiring parallel reduction include comparing two arrays or vectors, calculating the scalar product of two vectors, finding the minimum or maximum value in a set, summing or multiplying all elements in a series of numbers, or computing the LP vector norm. If you haven't seen the previous episode about the parallel for function, I recommend you watching it, especially if you are not familiar with lambda functions in C++ or using vector view in TNL. Let's start with a simple example of summing all numbers in array A. In C++, this can be easily implemented with these three lines of code. However, doing this efficiently on a GPU is very challenging. For those interested, I refer you to an excellent presentation by Mark Harris, which explains in detail how to implement parallel reduction efficiently on a GPU using CUDA. However, the result is several dozen lines of code, which is not something we want to write every time we need to compare two arrays or calculate a vector norm. Therefore, in this video, we will show how to perform parallel reduction in TNL easily with a few lines of code without compromising efficiency. Let's return to our example of summing all numbers in array A. Here we can see the original code written in pure C, and below we see the same code written using lambda functions. At first glance, this may seem like an unnecessary complication, but later we will see that lambdas offer a powerful tool for performing parallel reduction. We use two lambda functions here. The first one is fetch and is responsible for loading the data we want to reduce. This lambda function takes only one parameter, which is the index of the element it should read and return. The second lambda function is called reduction and performs the actual reduction of the data. It takes two numbers and returns their sum in our case, as we want to calculate the sum of all elements. The original for loop can now be rewritten simply by calling these two lambda functions. As we can see, we have moved the body of the original for loop in the lambda functions. Note that we had to initialize the variable result with an identity element, which is 0 for summation. It's a value that, when added to any number, returns the same number. For multiplication, the identity element would be 1, and similarly for other operations. We achieved that if we now wanted to perform a different reduction operation, for example calculating the product of all elements in array A, only the lambda functions and the identity element for reduction would change. The for loop itself remains the same. Now we can replace the for loop with the reduce function from TNL. It takes a template parameter device which indicates whether the reduction should be performed on the CPU or GPU. We then pass the range of indices for which we want to perform the reduction. Therefore, which indices the fetch lambda function will be called. Here it is the range from 0 to size. Next we pass the fetch lambda function, the reduction lambda function, and the identity element value for the reduction operation. For the reduction to run correctly on the GPU, we need to mark the lambda function as CUDA callable, which tells the compiler to compile them for both the CPU and GPU. To simplify the code, TNL offers predefined commonly used reduction operations as seen in this table. Plus for addition, multiplies for multiplication, logical AND for logical AND, logical OR for logical OR, bit AND for bitwise AND, bit OR for bitwise OR, min for minimum, max for maximum. These functors contain both the definition of the reduction function and the identity element. The entire reduction can be then written in this compact form. Here we only define the fetch lambda function, which we don't even have to name, and we specify its definition directly in the parameter of the reduce function. As mentioned earlier, the TNL plus functor replaces the reduction lambda function and the identity element here. Let's put this all into a fully functional example in TNL that can be found in the file 01 summation.cu. In the main function, we first prepare a vector of numbers we want to sum. This can be either vhost or vGPU, depending on where we want to perform the reduction. The essential part happens in the summation function here. First, we extract device and index types from the vector type. We then prepare the auxiliary function vview that we will need to access data inside the fetch lambda function. The reason for using vector view inside lambda functions was explained in the previous episode. A link to it can be found below this video. We then implement the lambda function fetch, where we use the vector view vview to read the data from the vector v, and subsequently we call the function TNL algorithms reduce, to which we pass the template parameter device, the range of indices 0 to vget size, lambda function fetch, and the functor TNL plus. The result is stored in variable sum, and we then print the vector v and the value of the sum variable. We can compile the example using TNL CXX, run it, and see that we get the correct result. In the example 02 apps.summation.cu, we show how to sum the absolute values of the elements in the vector v. Therefore, we change the definition of the vectors vhost and vGPU to contain negative values. The only thing we need to change compared to the previous example is the definition of the fetch lambda function. Here we simply add a call to the TNL apps function. We may compile the example, run it, and see that we get the correct result again. In the next example, we will calculate the scalar product or dot product of two vectors. Let's record the definition. For vectors u and v with components u1, u2, u3, and v1, v2, v3, their dot product is given by u1 times v1 plus u2 times v2 plus u3 times v3. The implementation using parallel reduction can be found in the file 03 scalarproduct.cu. In the main function, we need to prepare two vectors u and v, either uhost and vhost, ugpu and vgpu. We pass these to the scalar product function, and the only thing that changes is the form of the fetch function, where for index I, we load ui and vi using vector view, uview and vview, and we multiply both numbers. The rest is the same as in the previous example. We compile again using TNL CXX and run it. The next example is 04 comparison.cu. It shows how to compare two vectors. The comparison function receives two vectors, u and v. In the fetch lambda function, we compare the east element of vector u and the east element of vector v. The fetch lambda function returns a Boolean value. If the vectors are to be equal, all components must return true, which we can check by applying logical AND to all comparison results. We compile using TNL CXX and run it. Note that in the main function, we set both vectors to be the same for the CPU, which is here uhost and vhost, but different for GPU, which is here ugpu and vGPU. Therefore, the vectors are equal on CPU, but not for GPU. In the example 05 contains.cu, we test whether a given vector contains a specific value. The contains function accepts one input vector v and the value that we want to test in this vector. The fetch lambda function compares the east component of vector v with the variable value and returns Boolean value true or false. We are interested in whether true occurs at least once, which can be tested using logical OR on all the values returned by the fetch lambda function. We can compile and run it to see that the vector indeed contains the desired value. In the example 06 max.cu, we demonstrate how to calculate the maximum of the vector's component. This is very simple already. The fetch lambda function returns the is component of the vector v, and as the reduction operation we use TNL max, which selects the largest among them. We compile, run, and see that the maximum value is 9. Often we need to know the position of the maximum element in the vector. This is shown in example 07 argmax.cu. In the getArgmax function, we must call reduce with argument function. It has the same parameters as the reduce function, but allows us to return the index of the desired element. It differs in how it calls the reduction lambda function. Besides two parameters a and b, it also takes indices aidx and bidx, which correspond to their positions in vector v. Moreover, it does not return any value but only modifies the parameter a and aidx. It stores the maximum of a and b in a and the index of the larger of the two elements in aidx. If a and b are equal, it stores the smaller index in aidx. This ensures that we get the index of the first maximum element in the vector if there are multiple such elements. The implementation of the reduction lambda function is in optimized form. If element a is larger than b, we do nothing. Only if a is smaller than b, we assign b to a and bidx to aidx. If a equals b, then only if bidx is smaller than aidx, we assign bidx to aidx. Otherwise, we do nothing. The fetch lambda function remains the same, and we must also remember to pass the correct identity element for the maximum calculation operation, which is the smallest element for the given numerical type. The function reduce with argument returns a tuple where the first component contains the result of the reduction and the second component is the position of the resulting element. We compile the example, run it, and we see that the largest element is 9 at position 8 because we index from 0. Since reductions with argument are used quite often, TNL also offers predefined functors for some of them. These include min with arg, max with arg, and any with arg. The last one serves to find elements that meet a specific condition in case when the fetch lambda function returns boolean. Thus, we could easily modify example 05 contains.cu to also get the position of the element with the given value. I would like to emphasize that the previous examples only demonstrate how to use the reduce function. As shown in this table, all previous examples can be easily replaced with existing functions in TNL. In the last example, we will demonstrate an advanced use of the reduce function, specifically how to combine two kernels into one for a more efficient implementation. In some algorithms, we need to add a certain vector expression to a particular vector and at the same time determine how much we have changed the original vector. In our example, we will add the arithmetic mean of vectors u and v to vector v. First, we will precompute this mean into vector w, then add it to the vector v, and finally compute the appropriate norm of vector w. In the file 08 update and reduce.cu, we have two different implementations which we will compare. The first one is at the beginning of the update and reduce function and is a direct implementation of the previous relation. We compute the arithmetic mean of vector u and v and store it in vector w. Then we add the vector w to vector v, and finally we compute the norm of the vector w as a sum of the absolute value of its component and add it to the variable total update. In this example, we will measure how long the entire computation takes. For more accurate measurement, we perform the same computation 5 times. The more optimal variant is shown in the second part of the update and reduce function. Here we use the reduce function and realize that the fetch lambda function does not only serve for data retrieval, but can also perform non-trivial computations. In our example, we stored the arithmetic mean of the ith components of vector u and v into variable wi, then add it to the ith component of vector v and return the absolute value of the variable wi for the reduction itself. The rest is the same as in the previous examples. Here we choose a very compact notation to emphasize how easily sophisticated computations can be performed with reduction. We compile the program and run it. We see that on the CPU the reduction variant is 1.57 times faster, and on the GPU it is 2.46 times faster. The reason is not so much that on the GPU we combine two kernels into one, thereby saving the need to launch one of them. The much more significant effect here is that in the first case we calculated the arithmetic mean of the entire vectors u and v, and we had to store this result in memory. This is more clearly illustrated by the following two code snippets. They are essentially equivalent to the previous example if we were to implement it sequentially on the CPU. The code on the left is equivalent to the version without using the reduce function, while the code on the right is equivalent to the version using the reduce function. On the left, we work with an array w of size, which is stored in the CPU's main memory. If we were to perform a similar computation on the GPU, this array would be stored in global memory. Access to both the CPU's main memory and the GPU's global memory is very slow. In contrast, on the right, instead of an array w, we use a variable wi of type double. This variable is very likely stored in the CPU or GPU's register if we were performing a similar computation on the GPU. And because we immediately add this variable to the total update variable, there is no need to store it further in the slow main memory of the CPU or the global memory of the GPU. This way, we use less memory and reduce the amount of data that needs to be transferred from the CPU's main memory or the GPU's global memory. This, in turn, results in faster computation. This example generally demonstrates another advantage of using lambda functions and primitives for parallel programming such as parallel for or parallel reductions. Building parallel code from pre-prepared blocks, as is the case when programming with the BLAS library or in Python, often leads to performing computations on the level of entire vectors, and the intermediate results are vectors that need to be stored in memory. This is also shown in this example where we demonstrated the advantages of expression templates in TNL. Here we have to access the array dw a total of 3 times. In contrast, with the help of expression templates in TNL, here we access the array w only once. This reduces the amount of data transferred, which subsequently leads to more efficient computation. And this is all for today. We have shown how to use the reduce and reduce with argument functions for developing efficient parallel algorithms. I hope that you have found this video useful for you, and I wish you happy coding before we will meet in the next episode.